To understand virtual thread, let's run this example. In this example, what we do is we are running 10,000 concurrent threads. First, we are running them using traditional thread pool, platform threads, and for the next one, we are using the new virtual threads Project Loom that started from the Java 21. So let's run it and see that what it will give us. So in our example, what we do, right? In our example is very simple. In our example, we are just taking the benchmark from the start to the end, and we check that how long it took for 10,000 threads to run in the traditional if we are using a traditional thread pool or if we are using a virtual thread. And here what we do, so we are passing here executor, and we are passing here the number of the tasks, and we are putting the thread to sleep. We are here simulating the blocking IO operation, right? Let's say we are calling a DB, we are fetching some data from the database, or we are making an HTTP call, so we have some IO operation. So we are putting each thread to sleep for 1 second, and for each 1,000 thread, we are printing the value. So we are printing the task ID and the thread ID just to take the benchmark, how long it took for the 1,000 threads to complete, how long it took for the 2,000, 3,000, and so on. And at the end, when all the threads finish its work, then we are taking how long it took, we are taking the benchmark, and we are printing that. Let's run this example and see what it will show us. Let's run. It's gonna take a while, so I'm gonna pause here, and I am going to proceed after all these threads complete its work. Both traditional threads and the virtual threads completed its work, and now we have numbers, we can compare them. So in this case, the first one, right, for the traditional threads, we are running 10,000, we run the 10,000 threads, and it took us 52 seconds to complete that work, right? It took us 52 seconds. And if we compare exactly the same with the virtual thread, it took us only 1 second to complete. So it's a 50 times faster than the traditional threads. But now let's go understand where exactly that comes from, right? So in our case, we did one thing. Our scenario is in our scenario, for each thread, we have a blocking call. We have a blocking IO call. We are simulating the call here. Either we are calling a DB or HTTP call, and so on. Let's understand where that advantage comes from, right? First, let's understand what is the Project Loom. Project Loom was introduced as a part of the Java 21. So Project Loom is basically a long-term open JDK effort to simplify the concurrency. So it introduced two main features. The first one is virtual threads that we are reviewing right now, and then in our next episode we are going to review also the structured concurrency. What is the Project Loom, right? What is its advantage? Think of it as a Java's answer to the async await or the coroutines or the similar multithreading efforts in other languages. So what is in our case, right? What is the virtual thread? Virtual thread, basically it's a lightweight thread managed by the JVM. But to go there, to understand what exactly it means that it's run by the JVM, let's first understand how our traditional platform threads, how they exactly work. The way they work, so when we are creating a thread in Java, the way it works is that that thread is managed by the OS scheduler. So we create a thread, and the OS scheduler maps that thread one-to-one to the operating system thread, right? It's expensive because for each thread we are creating 1 megabyte. We are creating a separate stack, which is 1 megabyte, right? It's hard to scale beyond a few thousand threads at the time. And it's also for the blocking operations, the thread blocks itself, right? So we have one-to-one mapping. If we create a thread in a traditional platform threads, then it's a one-to-one mapping to the operation system threads. But what happened in case of the virtual thread? In the case of the virtual thread, we still have those threads, right? We still have those threads, but we are calling them carrier threads. And the carrier threads are, or they are still one-to-one map, one-to-one to our operating system thread. But on the JVM side, what we do is we are creating the virtual threads. All the threads that we have seen here, all the threads that we have started here, these threads are basically in case of the virtual thread, right? All these threads, new virtual thread per task executor, all these threads are virtual threads, and we can create as many virtual threads as we want for one carrier thread, right? I hope it's clear. So basically, we still create one-to-one mapping from the, if we create a, we still create a carrier thread, which one-to-one map to the operating system thread, but on the background for one carrier thread, we can create countless number of the virtual threads. So basically, if to summarize, we have each carrier thread is still, we are creating, it's a one-to-one mapping for the OS thread, and the virtual threads are parked and resumed by a JVM. So the reason why it was much faster earlier, because whenever we have input-output, whenever we have input-output operation, whenever we have a blocking call, in that case, JVM parks that thread, parks that virtual thread, and resumes that thread when that thread finalizes its work, right? So JVM handles the scheduling, not the operating system. It's virtual threads, they are ideal only for the IO-bound concurrency, which means that whenever we are making a call, whenever we are making external call, and whenever our thread is idle, then in that case, we can leverage the advantage of the virtual threads. Otherwise, let's say that if our application is the CPU bound, we need the more CPU power, then in that case, virtual thread don't have that much advantage. So, but how exactly virtual thread is parked and resumed, right? Let's take a very simple example. Let's say that the virtual thread start executing a user code, right? So what happens is that the virtual thread, let's say 42, it mounted on the carrier thread. So basically it mounted on the thread which is running on which is one-to-one mapping to our OS thread, right? So it executes user code and it's running on the CPU, and the step 2 is virtual thread hits the blocking call, for example, thread sleep, or let's say that the call to the external system or some blocking operation, right? So in that case, what happens is that the virtual thread 42, in our case, right, JVM intercepts that, JVM saves that stack frame on the heap. So in our case, we are in the traditional multithreading. For each thread, we are allocating 1 megabyte memory, right? In this case, we don't do that. We save the stack. We take the stack frames on the heap, which takes only few kilobyte. So now that the carrier thread 1 is freed now, so because JVM intercepted and freed that, and now we can perform other operations, right? So carrier thread returns to the JVM scheduler. So, and as a step 3, carrier thread picks another runnable virtual thread and runs it. So in our case, the reason why it was fast again, because all those seconds that the thread was idle, carrier thread was idle, it was running another thread, right? It was running another thread, while in the traditional, for the traditional multithreading, we have to wait for that thread to finish its work. So then now it's carrier thread picks up another virtual thread. Let's say it picks up virtual thread 87, and now let's say that our previous one 47, right? Let's say virtual thread 47 completes its work, and or let's say that the sleep time expires. So what happens is that the JVM scheduler remounts the virtual thread 42 to another carrier thread, right? It could be the same carrier thread, it could be different, and the virtual thread 42 resume its work. So that's basically it. So again, when we are starting a virtual thread, it carrier starts it, when it hits the IO bound operation, let's say that there is some blocking calls, then in that case it's the state of that thread, virtual thread, saved on the heap. We are parking it, and once it's finalized its work, another carrier picks that thread from the heap and continues its work. So as a result, what we have is our OS thread or a carrier thread is never idle, waiting for the IO operation to complete, or we don't have any blocking calls. And if we do that, which means that the virtual threads can be scaled to the millions of threads very easily. So if we compare I put here some comparison summary. So if we compare feature and the feature for the platform and the virtual thread, so they are backed by, platform thread is backed by OS thread, which means that the OS scheduler, but the virtual thread are managed by the JVM scheduler. For the stack memory, again, in case of the platform thread, we need to, for each thread, allocate 1 megabyte. We are creating a separate stack for each thread, and we need to create 1 megabyte. We need to allocate 1 megabyte memory for each. For the virtual thread, it's just a few kilobytes on the heap. So for the blocking behavior, it blocks the OS thread, and in case of the virtual thread, it parks and frees the carrier. So for the scheduling, it's again scheduled by the OS, and here it's scheduled by the JVM. And for the scalability, it can go as high as thousands, but in case of the virtual thread, it can go to the millions. It's a platform threads. They are best for the CPU bound, and for the virtual thread, as we have seen earlier, they are best for if we have a lot of IO operations, making HTTP calls and similar, making them connecting to that database. So then virtual threads are ideal for those cases. So key takeaways that Project Loom makes high concurrency simple and natural. Virtual threads are still real Java threads, just cheaper. JVM handles parking and resuming, freeing the operating system for more work. And the many virtual threads, few carrier threads, and we may have here millions of the virtual threads. For those threads, we may have only, let's say, 5,000 of the carrier threads, which are mapping exactly to the operating system threads. So when to use it, when to use the virtual threads, and when to not to use them, and use the traditional threads. As I mentioned earlier, they are best for the intense IO or IO apps. When we have intense IO in our application, for example, network call, DB call, or HTTP call, then in that case we should use the virtual threads. And when we should avoid to use them, we should avoid to use them if our app is doing the CPU bound tasks, which means that the image and video processing, compression and decompression, and the similar heavy CPU bound operations.